lecture. She's going to tell us, I guess, about SPTs and topological order on the lattice. Is that right?
Yeah, I'm happy to be here. Thankful for the organizers for giving me this opportunity to talk to you for the next 3 days. Unfortunately, I wasn't here for the first 2 days, so it might be the case that a lot of what I talk about today will overlap with what people talked about in previous days. But hopefully it will be kind of from a different perspective. So the plan is, in the first lecture, we'll talk about symmetry-protected topological phases from the perspective of their boundary physics and also from the perspective of their bulk physics and their symmetry defects and symmetry fluxes. And in the second lecture, we'll focus on SPTs in 2+1D and gauge those SPTs to get certain kinds of topological order, and then we'll relate properties of the SPTs to then properties of the anyons of the topological order. Hopefully in the third lecture, I'll talk about another way to get 2+1D topological order, which is in the math construction, it's related to the impulse center. In the physics language, we construct a string net model. And I know that Lorenz also already talked about string net models, but this will be from like a more in-detail discussion about like how do we actually derive the anion types, etc., from the input Gaussian category. But because it's a rather broad audience, I'll start off with some general statements about, in condensed matter theory, how do we understand and study kind of quantum lattice models. And this will all be in the context of very concrete models that you can write down and work out the spectrum and the eigenstates, etc. So we'll be studying everything in the context of quantum lattice models. So what that is has some inputs. The first input is a spatial lattice lambda. This is kind of a cellulation of your spatial manifold. And so in 1D, for example, you just consider a bunch of points on a line. And each of these points posts a degree of freedom. So it might post a qubit. This is just a two-dimensional complex vector space. And that gives you a Hilbert space for the total space, which is just a tensor product. In this lecture, we'll just talk about tensor product Hilbert spaces over all of these two-dimensional complex vector spaces. This can be more general. It can be some finite dimensional local Hilbert space. When it's a qubit, which is mostly what I'll talk about today, we can write down all the operators that act on this Hilbert space using the Pauli operators, which will feature a lot in this lecture. So sigma x on site j. And you tensor with the identity on all the other sites. And then sigma y. Okay. In addition to this, so I'm going to put qubits on the vertices of my lattice, but you can also, especially when you work with higher form symmetries, as Sal will do in their lecture later today, you can also consider putting these degrees of freedom on the links and the faces, etc. But for the purpose of studying zero form symmetries, I'll put them on the vertices. Then you have your symmetries. And today I'll just talk about the most vanilla type of symmetry. So this is going to be zero form, invertible, and I'm going to do internal symmetries, so no space-time symmetries. And I'm also going to study kind of finite symmetries. And so that's just a collection of operators that act on all of space. And then finally, you also have the dynamics given by the Hamiltonian. And so it's just a collection of local operators. Each of these is a subset of your lattice and might act on something like this, or like some 3 sites like this, etc. And we're going to study, in particular, gap Hamiltonians. So what this means is that this is a big operator, a big matrix. I can diagonalize it. And what you want is a kind of family of Hamiltonians such that in the thermodynamic limit, there is an energy gap to the rest of the eigenvalues. And there's a ground state subspace that hosts like a finite number of states. So this is energy. And in this context, we can consider phases of matter. So what's a phase? Well, we can say that 2 Hamiltonians are kind of equivalent. 2 gap Hamiltonians are kind of equivalent if you can interpolate them while maintaining this gap. And anything can sort of happen to the higher energy states. We don't really worry too much about them. But what you care about is that in a thermodynamic limit, you maintain a gap above the ground states. So if I have, so this is like a family of Hamiltonians given by, so H. We say that these kind of realize the same phase if you can interpolate them while maintaining this gap. However, if there's no interpolation that maintains the gap and you have to cross the energy levels in the ground state, then they're in different phases.
So you don't care about crossing above?
Yeah, so you just care, and the reason is because we're really kind of studying properties of the ground states. So what you can show, and it's a bit of work to show, but you can show that if you maintain the gap above the ground states, then suppose that this has some ground state spanned by some state psi of 0. You can show that this also has the same number of ground states because you don't close the gap. And every state, and then there's a mapping between ground states here and ground states here. So for every psi I of 0, you can kind of span this space by psi I of 1, where this is some finite time evolution of a local Hamiltonian. So that means that if you maintain the gap above the ground states, then there's no kind of big qualitative change in the ground states. And so the ground states here can be roughly mapped to the ground states here by just a local unitary. And there's a method to show that if you maintain the gap, you can just construct this local unitary. So this is a local Hamiltonian, you evolve it for a finite amount of time, so it really only changes local correlations.
So psi I are different ground states, degenerate properties.
Yeah, so for example, you could have some degeneracy if you have like topological order or spontaneous like zero from symmetry breaking, but then there's like a mapping between states here and states here.
In your picture, is it possible to also have continuous spectrum?
Yeah, so you aren't guaranteed that. So if you have a gap closing, so there's a continuum of energies above the ground state, then you can't guarantee this nice interpolation between the ground states.
I see. So it is allowed for some of these statements.
Yeah, so the kind of families of Hamiltonians we want to study today are gap Hamiltonians because there's a nice way to define equivalence between them and equivalence between the ground states. So we can define equivalence between Hamiltonians in terms of like maintaining the gap, and then equivalence on their ground states in terms of this like local unitary interpolation. Okay, so we'll also in particular study SPTs, which are kind of a particular way to are kinds of gapped phases of matter. SPTs so distinct SPTs are protected by symmetry. So a symmetry protected topological phase. So what that means is HA is equivalent to H. You can kind of interpolate between HA and HB, but only if you break the symmetry. So this is SPT. And so if HA and HB cannot be connected while maintaining the gap and remaining, keeping the symmetry, then they're in different SPT phases. And similarly, the condition under ground states is kind of psi I0 equals U psi I1, only if U breaks the symmetry. So this like for some So you can only really interpolate between these ground states if you break the symmetry. Okay.
Sorry, could I, sorry, keeping an F question, but when you do this, you fix the asymmetry group
Yeah.
in the whole
Yeah.
discussion.
Exactly. So when you talk about SPTs, you consider some symmetry,
Right.
and then you can consider gap Hamiltonians and the eigenstates that are symmetric under the symmetry. And then you can ask, can I interpolate between HA and HB by adding some perturbation, say, while maintaining the gap if the perturbation has preserved the symmetry? And it turns out that you cannot if they're at different SPT phases. Okay.
Excuse me, I understand something. I don't understand something that seems to be very basic. What if V is equal to 0?
Oh, if V is equal to 0, then they're just the same Hamiltonian. So they realize the same phase.
But, and then HA and HB would be the same,
Yeah, then HA is just literally the same as HB.
but you would still break the symmetry?
Then if HA has a symmetry, HA equals HB, HB has a symmetry, their interpolation is trivial so that they're in the same SPT phase.
You assume V doesn't commute with UG, and that's really.
Yeah, what I'm saying is like it's possible that there's a HA and HB which are different, and I'll show an example shortly. And to interpolate them while maintaining a gap above the ground state, you need to add a B that breaks the symmetry. Yeah.
Is this the only assumption such that the penultimate line is true?
This one?
Yes.
The assumption that you have to break the symmetry if you try to interpolate them between the Hamiltonians.
Sorry for holding this up, but if HA and HB are equal, then they are
In the same phase, yes.
in the same phase,
Yes.
and there's no need to break a symmetry. They can be the same.
You don't need to interpolate. They're just the same.
Exactly, but it's an interpolation that's trivial.
Yeah, exactly.
That's the only fringe case that's not covered by that statement.
Well, if HB is 0, then it always commutes with the symmetry. So,
Thank you.
So if I could just be a very annoying mathematician and just say it in my words, I think what you're saying is symmetry protected topological phase is an equivalence relation on Hamiltonians, given by the relation you apply. Right?
yes, yeah. Yeah, it's kind of like the space of connected states and stuff if you maintain the symmetry. Okay, so I'm going to be pretty concrete. So we're going to work with very explicit models. So in 1D, there will be, so in 1D, there is a very nice, simple examples of these SPT phases that are used in many different contexts. And so I'm just going to give you a flavor of what this sort of means in the context of some examples in 1 plus 1D and 2 plus 1D. So in 1 plus 1D, we can consider Z2 times Z2 symmetry. And as I mentioned before, each of these points is a qubit, so we can have a spin chain with site 0, 1, all the way to site L minus 1. And we're going to consider a spin chain with an even number of qubits. And now we can define our Z2 times Z2 symmetry, so let's call U even. And then we have U odd. Defined as follows. So U even is just kind of a spin flip on all of the even sites, and then U odd is a spin flip on all the odd sites. And in this context, we can write down two gap Hamiltonians. So one gap Hamiltonian, let's call this H1. So you can check that both of these Hamiltonians, I'll just keep my notation the same. Both of these Hamiltonians commute with both of the symmetries, and they're the simplest possible case. So there's a very nice kind of class of Hamiltonians that Lawrence might have talked about that are commuting projector. These are not projector, but they're still commuting. So that's when H prime equals 0. And these are very nice because you can easily solve for the ground states. So in this case, for example, the ground state projector, each of these, this has a unique ground state, and its ground state projector is just psi 0, psi. Just a projector onto all the plus eigenstates of sigma x. And then this one has a ground state projector that is, if you had this on periodic boundary conditions, then the ground state projector would just be this. And this would be a unique projector. But on open boundary conditions, what you find is that there are 2 to the L dimensional Hilbert space, and you have 2 to the L minus 2 Hamiltonian terms. So when you satisfy all of them, you still have a 4-fold degeneracy. And that comes from 2-fold degeneracy at each boundary. Okay, so these ground states are actually very simple to write down, and you can write this, as you all know, as just the state is just a +1 eigenstate of sigma x on every site. You can also write this as a sum over domain wall states. And you just sum over all of the domain wall states in the sigma z basis. Now, how do you write down this ground state? It actually takes a rather similar form. So this is H1, this is H2. So as I wrote down, that ground state has a sum over all of these kinds of domain wall states. And this one also takes a simple form. So what you can do is you can write this as some state that looks like.
Sorry, did you note that was size 0, not size 2?
Oh, sorry.
Sorry, Carol. Can I also ask about the notation? So there you have a bunch of pluses in
Yes.
the first line, and then you start with the bottom line. So you have plus and then proportional.
Yes, so this is the plus 1 eigenstate of sigma x on every site, and then this is eigenstate of sigma z. And this is proportional to because I want like a 1 over, to normalize this state. So there's just like a 1 over kind of 2 to the L over here.
Sorry, dumb question again. What are the domain wall states? What are you summing over?
Yeah, so I'm summing over, so all of the configurations in the sigma z basis. So a domain wall state is when you have a domain wall between up and down in the sigma z basis. So that's an so one spin has eigenvalue +1 under sigma z, and the neighboring spin has eigenvalue -1. And if you sum over all the possible domain wall states in the sigma z basis, then you just get this plus state.
So, sorry, so that dot there
Yeah.
are,
That means that I sum over all of the possible choices of this guy being up and down, this guy being up and down, this guy being up and down. So that's why there's 1 over 2 to the L
oh, I see.
number of them. Yeah. Okay.
Why are they called domain wall states?
Oh, because they include domain walls in the sigma z basis. Yeah. And so they're kind of domain walls because if you have like a symmetry broken state for this Z2 for a Z2 symmetry, then you can create a domain wall by acting with the symmetry on part of the system. So this is kind of a domain wall when you have a Z2 symmetry. But I can also write this psi2 in a very simple form. So on periodic boundary conditions, you just have all of the even states and you sum over the domain walls on all the even states, but the odd states are kind of conditioned on the even states. So when these two, so this is like, so site 1 and site 2 say, then this middle site 1 has to be plus because there's no domain wall between these two. However, if site 2 and site 4 have a domain wall, then site 3 has a minus in the sigma x basis. So this state site 2 you can write very explicitly. You just sum over all the domain walls on the even sites, and then the odd sites are conditioned so that when you have a domain wall on the even sites, you have a minus, sigma x minus, and then if you have no domain wall, then sigma x is plus. So there's a very simple way to write down all these states. And there will be kind of similar ways to write down SPT states in higher dimensions as well.
Where the summation is over all possible distances between the 0, 2, and 4.
So this is a summation over all the sigma z, j, like even. So this is kind of summing over all the sigma j even and odd, and this is summing over the sigma z, j even, and then the odd states are kind of conditioned on the even states. And then you can show that this Hamiltonian is minimized with this state.
So are these supposed to exhibit the two different SPT phases?
Yes, exactly. So now you can ask, okay, I've shown you the Hamiltonian, it's clearly gapped. I've shown you that they both have unique ground state on periodic boundary conditions, but how do you see that they're different SPT phases? So how do you see that they're not related by symmetric local unitary? Actually, I can also write this as I can also interpolate between these states. But you can see that this interpolation explicitly breaks the symmetry because sigma z doesn't commute with sigma z on the sigma x on the odd and sigma x on the even. Okay, so how do you see that they're actually realizing different SPT phases? Well, we're going to first talk about how to see that from their boundaries, and then we're going to talk about how to see that from their bulk symmetry defects. Okay.
Can I ask a question there? So you said the ground states for H2 are forward degenerate,
Yes.
but then if you transform them into each other, do they all get back to the same?
Yeah, so this is on periodic boundary conditions. There's a unique ground state for each Hamiltonian, and you can
So are we on periodic boundary conditions? Or
Yeah, so if this is this is periodic boundary conditions, and so initially you can consider the system on periodic boundary conditions, and for the second approach, which is the bulk symmetry defect approach, we can just use periodic boundary conditions. For the first approach, it's convenient to open it up into open boundary conditions and investigate their boundary modes. Okay. So the first approach to trying to understand what's the difference between these two Hamiltonians is to study their edge modes from their boundaries. So if we consider the system on open boundary conditions, we want the bulk of the system to be in the ground state. But as I mentioned before, for the second guy, H2, there's a fourfold degeneracy coming from each boundary because we have a 2 to the L dimensional Hilbert space, but we only have 2 to the L minus 2 constraints given by the Hamiltonian. And so the question is then, can we add any Hamiltonian terms to the boundary to lift that degeneracy? So for the first one, if we set all of the bulk terms to 0, then U1 and the U even and U odd just act trivially. So now for the second case, let's set all of the bulk stabilizers to be 1. And so that means that we set, for example, Z0 x1, Z2 equals Z1 x2, Z3 equals Z2 x3, Z4, all equal to 1. Okay, because we want to be in the ground state in the bulk of the system. And we just want to ask, can I add any Hamiltonian terms to the boundary to lift this degeneracy? Now, what you can do is you can multiply all of these.
You don't multiply, you set them equal.
Yeah.
You want to multiply them? Or?
Now, what I can do is I can multiply this guy with this guy, etc.
So you set them equal.
Yes, but when I multiply them, I'm going to get a global constraint that I'm going to use.
Are you talking about the eigenvalues or
I'm just going to say when I multiply this with this, and all of the ones where x is even, what I'll get is Z0, x1, x3, xl minus 3, Z L minus 2 equals 1, right? So if I multiply all of the odd guys, I'll get this constraint. If I multiply all of the even guys, I'll also get a constraint. Well, I get is Z1, x2, x4, all the way to xl minus 2, ZL minus 1 equals 1. Yes?
Or X and Z?
Sorry. So if I don't want to write a sigma, then I'll just write sigma z. Instead of writing sigma z, I'll write z.
Okay.
Yeah.
I'm sorry, Dave, what does it mean xj equal 1?
Oh, so this is saying that I want to be in the ground state. So I want to satisfy all the constraints given by my Hamiltonian, H1 up there. So I'm going to just set, and I know that the ground state is when all of the sigma x's is equal to 1 on the state. So the state is an eigenvalue of each sigma x with the eigenvalue 1. So I'm just going to set x.
So these eigenvalue equations you have on the top, on the next line, they are the operators.
Yeah, I'm gonna say that on my ground state, then all of these act as identity on that state. Yeah. Okay. And so I'm gonna consider all the states for which these all have eigenvalue 1. So I look like the ground state in the bulk of the system. Okay, so then what I can do is I can use this to simplify U even and U odd, right? So, so because U odd is basically a product of all these sigma x's on odd sides, and U even is also a product of these sigma x's on even sides. So what this implies is that the U effective U odd on states that look like the ground state in the bulk of the system is this. Okay, I've just plugged in this equals 1 and this equals 1 in those definitions of U even and U odd. Okay, so this is the effective action of the symmetry on states that look like the ground state in the bulk of the system. And you can see now I can write this as U tilde odd left or right, U tilde odd left, and this is going to be U tilde even right, U tilde even left. Because this is a product of an operator that acts on the left side of my spin chain, tensor product with something that acts way on the right side, so I can separate those two parts. And if I want to add Hamiltonian terms, then they will have to satisfy the even and odd separately because they're far localized from each other, and the Hamiltonian terms are local. But now what you can see is that the effective symmetry action on the left end of the system form a projective representation. And the symmetry on the right end of the system also forms a projective representation. And so, you know, that's an anomaly in 0 plus 1D. And you can see this because these two anticommute with each other. These two also anticommute with each other. So I think in Zohar's lecture, he mentioned projective representations as anomalies in 0 plus 1D. This is an example of the simplest such projective representation. In general, this gives you the non-trivial, different elements of this second cohomology class. And so this is reflecting the fact that there's an anomaly inflow structure. So these different SPTs also correspond to different anomalies in one lower dimension. And the anomaly is given by the anomalous representation of the symmetry at the edge. And you might ask, okay, so how is this kind of, so what this says is that when you have an edge of this SPT here, there's a protected degeneracy, there's a twofold degeneracy on each side that you can't lift, right? Because there's an anomaly preventing you from lifting that degeneracy with local Hamiltonian terms. You can't kind of satisfy the bulk Hamiltonian terms and also satisfy these boundary symmetries. And so then you can ask, okay, how is that? This may tell you that they're different in some way, but how does that relate to this picture of like classifying gapped Hamiltonians by interpolation while maintaining the gap, and classifying their ground states by interpolation by local unitary evolution? Well, you can imagine that if I had this will translate to kind of a degeneracy between, more generally, this is so this is an example of a degeneracy at a boundary with vacuum. But the more general case is you have this degeneracy between any interface between two different SPTs. So, boundary mode. So I might have like some big classification of different SPTs, and when I place two different SPTs next to each other, I will have typically this sort of like degeneracy or some gaplessness in terms of their edge modes, yes.
Can I try to make sure that I understand what's going on? So you have these original expressions for UE and U naught, and you impose the conditions in the second pole, and you get the expressions for U, E and naught tilde, and O rather, and then you do a computation and find that they do not satisfy the conditions of being generators of Z2 times Z2. That's the anomaly.
So what we find is that they form a projective representation. So this is, you can write this as U odd left tensor U odd right, because this is an operator localized far on the left end of your system, and this is an operator localized far on the right end of your system. And then if you look at the combination of both, you get an ordinary linear representation of Z2 times Z2. But if you look at each one individually, it actually forms a projective representation.
That's a computation one has to do that I'm not supposed to do in my head, or should I?
Yeah, so one way to see it is this guy. Let's do the left side. So this is our left symmetries, right? And you can see that now. Let's suppose that our representation of so this is like the 1, 0 element, and this is the 0, 1 element of Z2 cross Z2, right? And so now we also need a 1, 1 element. And so what's our 1, 1 element? We can say that is like, well, let's call our 1, 1 element, say, minus I or I y0 z1. And so now you can see that if I choose my 1, 1 element to be this guy, then this times this gives minus this guy. If I chose my 1, 1 element to be actually minus this one, then I find that this times this is minus the 1, 1 element. So in either case, you get a projective minus 1 phase. And then you can also say that you can take the commutator. So this guy times this guy times this guy dagger times this guy dagger should give you like omega. So this is saying UG UH equals omega GH UGH. This is our 1, 1 element. And then this is ambiguous up to co-boundary, And so what you find is that this taking this guy times this guy times this guy dagger times this guy dagger gives you omega GH over omega HG, which is minus 1 in this case, and that's a gauge invariant quantity that tells you about the 2 co-cycle. Yeah.
I should have asked earlier, but so right now you're trying to show that H1 and H2 are in different symmetry protected phases.
Yeah.
Now H2, with H2, you're pointing out that the ground state is fourfold degenerate, right? And the projective representation is occurring on this space, right?
Mm-hmm.
But is it on that somehow? It sounds like you're breaking it up into 2 different spaces, right? 2 different 2-dimensional spaces. Is that right?
You mean because there's yeah. So that's because I'm assuming that the bulk of my system is in the ground state.
Right.
And so then what I want to do is I only have kind of excitations and degrees of freedom I can manipulate at the boundary, and I want to gap out those edge degeneracies.
That's right.
Yeah.
I see. And that's so do you get a 2-dimensional projective representation in the end?
Yeah.
I see. I think I understand. But what I don't understand is on H1 side, these are also degenerate, therefore? Is there a fourfold?
No, there's no degeneracy at all. So for H1, right, I can just set all the x's equal to 1. And then there's a unique ground state for this Hamiltonian, even on open boundary conditions.
So I might be getting very misunderstanding something. So why doesn't this already prove that they can't be in the same topological phase? If one of them has degeneracy and the other doesn't.
Well, you might want to then relate.
So can I go from one to the other without breaching the graph?
Yeah, exactly. So you might want to relate that to this picture, right?
Right.
Yeah. So not going to go through all the details, but maybe you can convince yourself that from the perspective of interpolating between the states,
Right.
there's no interpolation between these two states that maintain the symmetry. And one way to think of that is, one way that you would try to interpolate between these states is, this is in terms of the boundary, but you can also derive a degeneracy when you have kind of an interface between these two SPTs. So if I put SPT A on the left side, so this is H1, and H2 on the right side, then there's some degeneracy in the middle. Because you can also derive this projective representation at the interface. And so the most naive thing to do, or one way to do if you have a symmetric gap boundary between these two phases, is you can apply a local unitary operator that basically nucleates. You start off in, say, phase by the ground state of H1, and then you apply a local unitary operator that sort of nucleates patches of phase 2 in one step, and you can do all this simultaneously. And if there's a gap interface between all these, then this is just a symmetric operation. And then in a second step of your local unitary, you can kind of connect all of these and remove the patches of H1. And now you've gotten into H2. So this is H2 that you've nucleated out of H1. So what I mean to say is that it's not obvious, it's not completely obvious going from the edge modes to like how we define phases up there, but you can show that if there is a protected edge mode, then at least this method of trying to interpolate between the two different states fails. You can't just take one state, nucleate bubbles of the other state, and then get into the other state. And more generally, you can actually show that you can't interpolate them but that takes more work.
I think I understand that, but I'm sorry, this is really ignorance. But if I go back to the picture up there, if I have two things that are connected by the family of Hamiltonians,
Yes.
I thought you'd already explained that the ground states are isomorphic.
Yes.
So why isn't that already sufficient to see that these two can't be in the same
Oh, because you can see that, suppose that I wanted to interpolate between these two.
Right.
So then I can write that as like, I can write my interpolating Hamiltonian as H of S equals 1 minus S H1 plus S H2. So as S equals, when S equals 1, then 0, then you have H1. When S equals 1, you have H2.
So somehow.
And then that Hamiltonian actually, so this is a symmetric Hamiltonian because we know that both of these terms preserve the symmetry, so their sum also preserves the symmetry. But this guy has a gap closing. And so you can also show that the other naive thing to do is to define my H of S using this unitary. So let's call this. The other naive thing to do is to define H of S equals, and then let's call this U of S. We're just working on periodic boundary conditions, so at least they have the same ground state degeneracy. Then I can define H of S equals U of S H1 U of S dagger. And you can also show that this guy at S equals 0 is H1, and at S equals 1, it's H2. This maintains a gap clearly because for every S, it has the same spectrum as H1, which is gapped. However, this U of S breaks the symmetry. So that means that for any S besides 0 and 1, this Hamiltonian also contains terms that breaks the symmetry. And so you can interpolate them if you break the symmetry and you maintain the gap, or you can stay symmetric, but you will close the gap. And it turns out that there's no way to actually connect these two Hamiltonians while maintaining the gap.
Right, but I'm sorry about this, but I'm still trying to understand a kind of contradiction. If this second statement is true, right, how could one have a unique ground state and the other have a degenerate ground state?
Oh, yeah. So what I'm saying is that, like, this What's that second statement? Sorry.
The second statement, I thought that the ground states with a non-gap family, right, have to be isomorphic. Isn't that what you said earlier?
Yeah, at least on closed boundary conditions. So
Oh, I
yeah,
see.
on periodic boundary conditions, they have the same
That is,
ground
I
state
see.
identity.
So that's the issue.
Yeah.
This statement that you wrote up there is not true for.
Yeah,
open
we want to kind of look at like the bulk gap of the system usually. Like even gap phases, we sometimes allow gap closing along the boundary. So sorry, I should have specified. Yeah. Yeah.
So is the general statement that two systems have share the same edge anomaly and don't have a ground state degeneracy, then they will fall into the equivalence class? Is that right?
Yeah, so you can more generally relate this sort of equivalence to a condition, at least for short-range entangled states, about like whether if you have an interface between these two states, whether you can get rid of whether you can have a symmetric gapped boundary between these two phases. Yeah.
Maybe I'm just too naive, but is it not enough to see from the edge that when U0L and UDL anti-commute in this case?
Yeah, so that's kind of one observation, but then you might want to connect that, as we mentioned before, to this kind of interpolation by Hamiltonian and interpolation by states. But I didn't go much into detail there, but maybe you can convince yourself on my sketched up argument, and to actually do that formally takes a bit more work. But at least you can see that there's ways to distinguish them in terms of like the edge modes, and also now I'm going to talk about a way to distinguish them by their symmetry defects. Okay, so the second approach is just purely in the bulk. So we just have a system on periodic boundary conditions, and so we don't have access to these edge modes, but we still want to ask how do I distinguish between these two SPT phases? So one way to do that is to insert a symmetry defect and ask how do they look different in the different phases. So what a symmetry defect does is it on periodic boundary conditions, it sort of inserts the Z2 flux through the cycle. And so you can do that very concretely in a Hamiltonian model in the following way. So we consider our system on kind of periodic boundary conditions, and let's define an interval A. And also another interval B. And what we want is that the size of A and the size of B and the size of A intersect B is much, much larger than. By range of Hamiltonian, I just mean the Hamiltonian consists of a bunch of local terms, and all these local terms act on intervals that are no longer than some range R. So I want these regions to be much larger than the size of the local Hamiltonian terms. And so to insert a symmetry defect, what you can do is you take your original Hamiltonian and you conjugate it by the symmetry restricted to region A. So what we can do, for example, if we want to restrict the symmetry U even to region A, is we can define U even A is just kind of, it acts in the same way in the region A, and it acts trivially outside of A. Okay? And to insert a symmetry defect, we can define H defect. And I'm going to insert a defect. I'm going to call this site 0. So 0. So what HB is the restriction of the Hamiltonian to region B. So what you can see what this is doing is it conjugates your Hamiltonian by the symmetry action along this interval. But then you kind of want to get rid of how it modifies the Hamiltonian in this region B. So that's the purpose of the second term here. If you had a semi-infinite system, then you can just kind of conjugate the Hamiltonian on half of your system. But if you want to do this on periodic boundary conditions, then you sort of need to undo the action of the symmetry transformation along this this other endpoint. So you can see that if H is symmetric, right? So each of the terms in H commutes with the symmetry. Then this UE, this conjugation by the symmetry restricted to region A, can only really modify your Hamiltonian near the endpoints of A. So what this will look like is it will look like H plus delta H0, where the modification of H is only localized near this site 0. A simple example is when you have
just when you write HB, when you say X is in B, there is going to be also some sort of boundary which tells you, I mean, there could be some nearest neighbor thing between the edge of B and the
yes, I'm just going to take I'm going to assume my Hamiltonian has finite range. I'm just going to take the subset of those Hamiltonian terms that are fully supported in region B. Okay, and so you can see that, for example, if you had an Ising Hamiltonian, and you had an Ising symmetry, so then what this will do is this procedure will just flip the signs of one of the couplings. It will flip the sign of this coupling between j equals 0 and j equals 1. So if you do this exercise with that, you'll find that H defect 0 equals H plus 2 Z0 Z1. And so you can see that you flipped the signs of one of the couplings, and so this will be like all of the ZZ terms will come with a coefficient of -1 except for the one here. What that is indicating is that you've inserted a Z2 symmetry flux, and so now you're on periodic twisted boundary conditions twisted by that Z2 flux. And you can also see that as you go around, what this does is basically as you go around the cycle, you pick up the symmetry action. Okay, so this is a symmetry defect, and this is a concrete way to insert a symmetry defect given a local Hamiltonian and a symmetry action. Now,
in the Ising example, what comes out for H defect 0 does not depend on the choice of the regions A and B.
Yeah, so as long as this regions A and B and the intersection of A and B are all large compared to the range of the Hamiltonian, then there will always be one Hamiltonian term that has a flip sign. Then it will only have one coupling that flips the sign. Is that your question?
That's a computation.
Yeah, you can show that. Yeah. Basically, because all of the Hamiltonian terms that are fully supported in region A all commute with the symmetry, so they don't get modified. The only terms that get modified is the coupling at the boundaries, and so what the coupling at the boundary does is it gets a minus sign because Z0, Z1 anticommutes with the symmetry restricted to like an interval between stretching from site 0 to somewhere else. Yeah.
Why do we need like two regions, A and B, to have this defect?
Sorry?
Why do we need to define two regions, A and B?
So I wanted to define B so that I could undo the action of the symmetry transformation near one of the sides. So I've only inserted a single defect. Otherwise, you would insert two, or like one and its opposite. You would insert a G and a G inverse on the other side.
Sorry, do you assume that region A starts from 0?
You could, but you could also pick another point if you wanted to. These defects are kind of topological, so you can move them.
So we don't assume.
For concreteness, I just put it at a particular site, but you can also move these defects, and they're equivalent to each other. Like that, if you wanted to move the defect to site like 1, basically what you could do is you could conjugate this Hamiltonian by a local unitary, so it's just equivalent to a different Hamiltonian with a defect slightly shifted. Okay, so how do we see that the symmetry defects are different for H1 and H2? So for H1, any defect, H defect, and I'm always going to put the defect at site 0 just for concreteness. Even equals H1 equals H1 defect. Odd. So you can do this exercise, and what you find is that the H1, the defects really don't do anything to the Hamiltonian. So H1 is, if you do this procedure, it will come back to itself if you try to insert a defect of the U even or the U odd symmetry. However, if you do this with H2, what you find is H2 defect
What is H2 here for this example?
Oh, I'm going back. I'm still looking at the same example. Yeah, we're just looking at it from a bulk perspective now. Yeah. So H2 defect even equals is modified.
What does the index E even mean?
Oh, because we have two symmetries. So I could have inserted a UE defect or a U odd defect. And so this is going to be, I'm just going to focus on one of them, which is the E defect. But the odd one looks a similar story.
So, sorry, Carolyn, and on the top blackboard, this H defect comma 0, is that the location of the defect 0? Or?
Yeah, so in this one, I'm just going to, I specify the site 0, but in all of these, I'm just going to assume that I put the defect at site 0.
So that's 0 up there and O down below, right?
Yeah, this is referring to now the specific symmetry because I had two different symmetries in the previous problem. Yeah.
So the last line is a definition.
This last line is what you would get if you did this calculation with H1 and H2 and U even and U odd. So this is kind of my definition of a defect at site 0. And then what you can do, and this works for any Hamiltonian, right? Any local Hamiltonian, you can plug this in as long as the regions of A and B are sufficiently large compared to the range of the Hamiltonian terms. And then this is what you would find.
So the E for even could appear on the left-hand side in the definition of H defect 0.
Right. So this is a general statement. So let's suppose that you had any. I'm going to put it at site 0, and I'm going to have any group element G. And then what you can do is something like this. Yeah. And that will be the insertion of a G defect. Okay, so what this looks like is like some of j is not equal to 1, z j minus 1, xj z j plus 1, and then plus z 0 x1 z2. And so now what you can do is you can look at the ground state projector. As we wrote here on periodic boundary conditions. And what it will look like is product over j is not equal to 1 plus z j minus 1. So you just flip the signs of one of the terms. So what is this? Let's call this prime because we've inserted the defect. This is just z1 psi 2 psi 2 z1. Right? You can show that this state is just the original ground state conjugated by these poly z operators on site 1. What that does is it will flip the sign of this term. So now this defect state has an additional charge under the U odd symmetry. So what you find is that in this kind of SPT phase here, the insertion of a defect for the U even symmetry will insert a charge of the U odd symmetry. So you can also show that this charge is related to this minus 1 given by the charge of the U odd symmetry is related to this omega hg over omega gh equals minus 1. That's measuring basically the fact that now when you've added the defect, you've gone into the minus 1 sector of the other symmetry. So you've inserted a Z2 charge. Okay. So this is just saying that you have these two different SPTs. There's a way to detect them by finding the anomalous representation of the symmetry on the edge, which prevents you from giving out edge modes. You can also detect their difference by the fact that one of them doesn't do anything when you insert the symmetry defects. But the other one, the insertion of a symmetry defect for one symmetry inserts charge of the other symmetry. And if you work a bit harder, and we'll also discuss some of this tomorrow, especially in the context of 2+1D systems, this also is indicating that now if both of these Hamiltonians have a Z2 times Z2 symmetry, but if you gauge that Z2 times Z2 symmetry, then the resulting theory will be different for the two different theories. And that's also indicating that they're not in the same phase. Okay. One nice thing that we'll use in the study, especially in 2+1D, is that there's also kind of a state perspective on this defect insertion. So if you have a state that is symmetric, meaning it has a symmetry and the symmetry isn't spontaneously broken, it doesn't have long-range order parameter for that symmetry, then there's also kind of a state perspective for what's going on here. So the state perspective is that if I have a symmetric state, so let's call this psi, and this psi can be either psi1 or psi2, it's just some symmetric state, and I act with U, E, A, so where the region A is some interval, and left and right are the right endpoints of that interval. So if I act the restricted symmetry operator on my state, then that's equivalent to acting with local operators on the left and right ends of the interval on my state. And this is just reflecting that there's kind of, in the symmetric phase, then there's kind of a dressing of this disorder operator that kind of stabilizes this state. So, or equivalently, there's this is related to kind of counter terms in quantum field theory that you can add. So what this means is that now what I can do is if I want to instead do a symmetry transformation on my state and leave the rest of the state looking like the ground state, so what this does is it creates excitations at left and right endpoints. And now I'm going to remove the excitation at the left endpoint. So I only have an excitation at the right endpoint. Looks like the ground state everywhere else, but there's a symmetry action on this side of the system because you've acted with U on the left side of the system. And so now you can see that this is a modification of the right endpoint. And if you now work this out with this ground state psi 1 versus psi 2, what you'll find is that this is going to be, so for psi 1, O, L, and O. Because the product of x on an interval acting on those states, it just gives you back the state. However, with psi 2, O, L equals, let's call this an interval from, this is U even A equals x to x4 to xl. 8 for concreteness. Then this will be Z1 and OR will be Z. So you can work this out because the stabilizer, like these, we all know equal to 1 on the ground state, right? So then you can show that the symmetry action of this guy on psi 2 is equal to OL, OR on psi 2, where L and R are both sigma Z operators. And so now you can see that the insertion of the symmetry defect here, which is just Z1 U E A psi 2 is equal to Z9 on psi 2, which flips the Z2 sector of psi 2. So this is a perspective that you can take just working in the ground state space. And what this also indicates is that there's a string order parameter for this SPT phase, because when people talk about string order parameters, they're referring to something like this. It's kind of a restricted symmetry operator decorated by charges. And so this is what people sometimes call string order parameter. Okay, so that's all for 1 plus 1D. Any other questions about the 1D story? Yeah.
So, given a spatial symmetry operator which has x, reconstruct the defect Hamiltonian such that it's still symmetric under that. So we write so H defect is a bit mysterious right now to me, but are you writing it such that it has UE of A as a symmetry?
Oh yeah, so good question. So if the symmetry is abelian, then clearly if H commutes with the symmetry, this whole guy commutes with the symmetry. And then if it's not abelian, then you have to work out the group multiplication there.
But the principle still is H defect is symmetric under this like finite interval symmetry. Is that right?
What do you mean by H defect? Is which finite interval symmetry are you talking
UE of A, or it's not being generalization.
Oh, you want to ask if this is symmetric under U G of A?
Yeah. That's right. Well, like, is that the point? If that makes sense.
So this UG of A is purely, the point of the UG of A is to insert a symmetry defect at site 0, right? And so, yeah, then if G is not abelian, then the action of UG, like then U H A dagger H defect G will kind of look like a GH defect. We'll insert a GH defect there.
Ask another question.
Yeah.
Sorry. So can I think that the transition from one SPT to another in different symmetries is easily simulatable, in contrast to when you move from one gap phase to another gap phase through a phase transition?
So transitions are always kind of hard to simulate if you want to do it on a computer. Maybe what you're saying is that because there exists a gapped path that breaks the symmetry, you can get between them if you allow yourself to break the symmetry. And you can get between them by a gap path, so maybe that's what you mean by easily simulable.
That's right.
Yeah, so they are kind of different from other phases. For example, transition between symmetric and SSB, etc., where there's no going around a gap closing. Yeah.
That would be exponentially hard, but here we can do it with finite resources.
If you break the symmetry. Yeah.
I presume in general, even if you don't break the symmetry.
Well, I guess the idea here is that if you don't break the symmetry, you have to close the gap to get between these two Hamiltonians.
Yes, that's right.
Sorry, could I just ask a terminology question?
Yes.
So this quantity at the bottom is what you're calling the string order parameter? Why is it called the string order parameter?
It's called the string order parameter because it looks like an order parameter, but it comes with this operator string. So it's, order parameter is kind of a correlation function between two local charged operators. But in this case, you also have a string, like this is not just a local order parameter, it's kind of a string operator that you're taking the expectation value of.
You mean that operator in the middle, you're calling that a string operator?
Yeah, so this is an operator that acts like x, 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 and then z, z on the endpoints. So it's not just like a local two-point correlation function.
I see, because there are all these local operators.
Yeah, it's like a string operator. Yeah. Okay. So. In the remaining 15 minutes, we'll talk about 2 plus 1D. A lot of the tools that we developed in 1 plus 1D are just as valid in 2 plus 1D, but I'll introduce another tool as well. So in this setting, when you have Z2 symmetry in 2 plus 1D, there's a kind of beautiful work that outlines the difference between these SPTs. It turns out in 2 plus 1D for Z2 symmetry, you also have a Z2 classification of SPTs. And again, we can consider a quantum lattice model. And I'm going to consider this kind of lattice and place degrees qubits on the vertices again. And again, we can consider two Hamiltonians that have a unique ground state on any closed manifold. So they're again kind of trivial they're again paramagnets under the symmetry. So similar to the 1 plus 1 decrease, we can consider an H1, which is just minus sum over J xj. And then similar to the 1 plus 1 decrease, we have another Hamiltonian that is slightly modified. So what this term looks like is it looks like so what this does is this BP term has a sigma x, poly x at the center, but it also has an I to the 1 minus zkzl for every pair of these guys on the boundary of this plaquette. So what this BP term is supported kind of on these 7 qubits.
What is the index P?
P is labeling the plaquette. So this is like P, one P, and then another P would look like P supported here, etc. And again, these two have rather simple ground states. So this has a ground state. If you just consider the system on a closed manifold, then this has a ground state psi1, which is just again a sum over all of the domain wall configurations. So what this does is it acts with a x, sigma x here, and then it acts with this 2 qubit coupling along each of these pairs along the boundary. And so what the purpose of this guy is it's trying to measure domain wall parity. So you can see that this guy is going to be a -1 whenever you have 2 domain walls that cross through this region. Because then you'll have like an up, down, up here, and that will pick up 2 i's, which will give you a minus sign. And so that will be reflected in the ground states of the 2 Hamiltonians. So in the first Hamiltonian, the ground state just looks like a sum over all of the domain wall configurations. And so to just kind of illustrate this pictorially, this is like the all up state with sigma z bases plus like the up state with a domain of downspins, plus the up state with like 2 domains of downspins, etc., appropriately normalized. Now, this guy has a slightly different ground state. So if you look at this ground state, this is equal to, again, you have the up state, but then when you insert a single domain wall, it comes with a minus sign. And then when you insert 2 domain walls, it again comes with a plus sign. So this is going to be like a sum over domain wall configurations. But with a negative kind of fugacity. So with each of these domain wall configurations in the sigma z basis, there's a minus sign if there's an odd number of domain walls, and an even sign if there are an even number of domain walls. And you can work that out by looking at how these BP terms are like counting how many domain walls come in through this plaquette and out through the plaquette. So if there are an even number of ones that go in through this plaquette and out through the plaquette, then you get a minus sign. If if there's a like 4n times, if there are 4 domain walls that come in and out, then you get a plus sign. Okay, so it's a simple difference by some signs, but we'll see that that actually leads to kind of dramatically different properties of their boundaries and their symmetry defects and symmetry fluxes.
Is the choice of the lattice just convenience, or if you do square lattice?
Yeah, you can also do it for other lattices. This choice of lattice is kind of convenient because the way that they got this model was actually from ungauging the string net model. So I'll talk about tomorrow how I'll talk about how if you gauge this model, you'll get a Tor code, a Z2 gauge theory. If you gauge the symmetry in this phase given by this guy, you'll get a double semion or twisted Z2 gauge theory. And then when you write down string net models, it's convenient to work on trivalent lattices because then you can implement the fusion rules. And so you can see that the kind of dual lattice here is trivalent. And so that will be convenient for when you gauge the symmetry, it will be on a trivalent lattice. But indeed, you could also define it in more general lattices. Okay, so for the sake of time, I'm going to talk about the boundary a little bit quickly, maybe. For the boundary, we also want to show that when you have a boundary in this 2 plus 1D case, you have an anomalous representation of the symmetry similar to the 1 plus 1D case, where we got a projective representation of the symmetry. So similar to the 1 plus 1D case, you can show that now you have a global Z2 symmetry, which is just U equals product over J xj. However, if you have a system with boundary, then similar to the 1 plus 1D case, you want the system to be in the ground state in the bulk. And then when you project into that kind of subspace, so you only allow excitations near the boundary, what you'll find is an effective symmetry action near the edge. So now if I have my system with a boundary, so this is, you'll have a U boundary, which is just supported in the 1 plus 1D boundary. Similar to in 1 plus 1D, we got an effective symmetry action supported in 0D, 0 plus 1D. I won't go through all the details, but what you'll find is that for H1, you'll find U boundary is just trivial. Similar to the trivial paramagnet in 1 plus 1D. But for H2, what you'll find is that U boundary looks something like this. And so this is symmetry in 1 plus 1D. And it isn't just a product of sigma x on every site. It comes with this factor. And you might think, oh, there's an I, so why is it a Z2 symmetry? But on any system with periodic boundary conditions, which you will have on a system with boundary, this is periodic, there's a -1 to the number of domain walls. And you always have an even number of domain walls, so this is always plus or minus 1. So this is actually a Z2 symmetry in 1 plus 1D. Okay, so then, now given the symmetry action, you can ask, how do I extract something like an H3 class or anomaly from the symmetry action? There's a nice paper by Els and Nyack in 2014 that tell you how to do this. The basic idea is that when you have, this forms a 1D representation of Z2. So when you square this guy on periodic boundary conditions, it's equal to 1. But now you can consider the restriction. Maybe I should put boundary lower. But now you can consider the restriction to U boundary restricted to region A. So you just include all of the terms in this guy that are supported in region A, where A is some interval. And now the group law no longer holds near the boundary of A. So what you find is that U boundary G A, U boundary H A equals omega G H U. So clearly they have to compose according to the group law in the bulk of A, but there can be local modifications near the boundary. So omega is supported on the left and right ends of A. This happens for any kind of truncation you have, and of course there's some ambiguity in the truncation. We'll see that that will lead to this ambiguity of the three cocycle by coboundary. Okay, so this is just saying that when I restrict my symmetry action, and it's not just like a completely on-site symmetry, so there's some operators left over when you try to compose the restricted symmetry operators. And now what you can do is you can consider composition of three symmetry operators. And we can first pull these two guys together, fuse these guys together, or fuse these guys together first. And we'll see that this one will give you omega G H U boundary G H A U boundary K A. And now we use the same thing again to fuse these guys together. So now this is equal to omega G H omega G H K U boundary G H K. On the other hand, we could have also fused these guys first and then fused it with the rest of the guy. So then this is equal to U boundary G A omega H K right? And then if you work out the algebra, what you'll find that this means that this guy is equal to U boundary G A omega H A. So this is the equation that you get. And this holds exactly when you include omega left and omega right, right? Because omega is supported on the left and right endpoints of this region A. So you can write this as omega left G H, omega right G H. However, this equation only needs to hold up to a phase when you replace each of these by left or each of these by right. So if we replace this by, say, left, 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 then what you find that this only needs to hold up to a phase, which is this 3 cocycle. You can relate this procedure more directly to this, like this kind of fusion rule. As well. But maybe for the moment you can convince yourself that this gives you the 3 cocycles. Now what you can do is you can apply this formula to this representation of the Z2 symmetry. And what you'll find is that this omega GH is basically going to be a Z on this left side. Sigma Z operator localized near the left side. And then this is going to be trivial. And what you'll find that this is a sigma Z that will anticommute with this guy. So you'll get a minus z left. And so then this minus sign is your omega gh. So this is equal to minus 1 for this symmetry.
I'm sorry,
Yeah.
I got a bit lost. In the definition of U boundary, this is a product over xj where j runs over what?
Yeah, the U boundary you get in a similar way to what we did in 1 plus 1D, where we got an effective action in 0D by insisting that our bulk is in the SPT ground state, right?
Right.
And so then if you do the same exercise in 2 plus 1D, you'll find that for this H2, what your U boundary will look like is an effective symmetry action in 1 plus 1D, and it looks like this.
So it's just acting, it's a product over various operators, just acting on states on the boundary,
Exactly,
on sites
yeah.
on the boundary.
Yeah.
And you're still acting, when you write these equations, you're still acting on the ground states of these two Hamiltonians, but in this case, H2. Right?
Yeah, the bulk is in the ground state. But what you find is that for this H2, you have a massive degeneracy near the boundary.
Oh, I see.
And so now what you're trying to do
That's
is you
where
get,
you're acting, I see.
yeah, now you have a boundary representation of the symmetry, and you ask, can I add terms near the boundary that are symmetric and gap out that kind of extensive degeneracy near the boundary? And you find the answer is no, you can't get out all the degeneracy in a symmetric way because the representation of the symmetry at the boundary carries an anomaly.
At the beginning, you said this is Z2 symmetry?
Yeah, there's a global Z2 symmetry, yeah.
So what are the G's here?
This is the effective symmetry action on the boundary. So this is the 1 plus 1D symmetry.
And those G's are all non-trivial probably, right, in that omega?
Oh yeah, sorry, this is all the non-trivial element of Z2.
Ah, okay.
Yeah, exactly, sorry.
Okay.
Yeah, so what you find is that this is this 3 cocycle is a non-trivial element of this H2 classification, and this is indicating that these two are actually different SPT phases, and they describe inflow from this SPT describes inflow from this anomaly here. Okay, so I don't have any more time today, so I'll talk about symmetry fluxes and anyons tomorrow.
Any further questions? So here I guess you kind of, in the 1 plus 1 and 2 plus 1 case, you've kind of gone in detail over the simplest example, right?
Yeah,
Using
yeah.
this non-trivial SPT. So if we want to generalize this to general groups, is it sort of straightforward how to construct these Hamiltonians? Has this been done in this paper of 1182?
Yeah, so I guess one question is, we know the classification from a kind of higher level mathematical perspective. So one question you might ask is, do we know how to construct Hamiltonians that realizes each of these phases? And the answer is that for low dimensions, and also for general dimensions for certain classes of SPTs, we know how to construct them. So for example, all the ones described by group cohomology, all the bosonic ones described by group cohomology, there's a systematic way to construct these Hamiltonians. But then there are also...
So for any group, any finite group, basically.
Yeah, but then there are also kind of beyond group cohomology SPTs, and the lower dimensional ones, we also know how to construct them, but I think that in higher dimensions, there's not like a general approach to constructing lattice models for them. Similarly, like for fermionic cases, there are ones that are in group cohomology and ones that are in group supercohomology. Those we kind of know how to construct, but the ones that are beyond group supercohomology, those lattice models were only constructed recently, and there are probably ones that we don't know the lattice model.
Okay, so I think we'll have a little break, and then at 11 we'll come back with some tutorial sessions. Thank you.